Yes. No, I'm also away from writing footage. Yeah. Actually.
Okay, that come up as recording.
Yeah, that's cool.
Okay. Okay, guys, we might make a start. This is going to be a really ordinary sort of introduction to Oleg, because I don't know him, and Michael's crook. So can you do the introduction? So I just quickly pulled some stuff off with the web for those who don't know him then. I'm not going to do the introduction justice, but Professor Oleg, you started your postdoc journey, I should say, in all sorts of renowned institutes, including the University of California, Berkeley, and the Lawrence Berkeley National Laboratory. He's now chair of the computational condensed matter physics at EPFL, and I'll keep it short because hopefully everyone has seen what all that stands for. His current research focuses on the theoretical and computational physics of two-dimensional and topological materials, with a strong emphasis on their respective technological applications. And from what I can understand, your recent efforts, or your team's recent efforts, which is directed towards materials discovery by means of high-throughput computational screening, resulted in prediction of several novel topological insulators and semimetals that received full experimental confirmation. So I'll hand it over to Oleg to put the detail on that very short introduction.
Okay, thank you so much for introducing. I do hope all this setup now works fine. It took us a little bit of time to figure out, to sort out all the problems. So I'm really grateful for the opportunity to speak in front of this community in Melbourne. I mean, it's a little bit of a spontaneous visit. I also see that there are some people from Sydney. Just in case, I was also asked to give the same talk also on Tuesday next week at UNSW at 4 o'clock. That said, when I've been thinking about fleet and about the research interests here, I mean, this is the topic I suggested. This is not the only thing we do in my group, topological materials. We also are active in let's say, conventional 2D materials like graphene, and I mean some other, let's say, unconventional magnetic systems, and so on and so on. But and for this particular talk, many of the works that were published, I mean, not the freshest ones, so some of them already a few years old. Nevertheless, it makes still a very nice story, and this is what I would like to share. So, as Jason introduced, we do computational physics, so there are no experimental activities in my group. And with this topic, we actually had an opportunity to do, let's say, computational science that is slightly closer to the experiments. So this is typically the slide I'm, okay, hold on, I need to somehow move the point. And
then
hide
meeting controls, hide plate down.
Okay, very good. So I have to now rewind back one slide. So this is the slide I'm typically showing when I start my talk, and this is, let's say, a rough timeline of the field of topological materials starting from 2005, basically 20 years back. And please move this window away from the shared application. I don't know what. Yeah, I mean, it just appeared. I don't know what does it mean. Okay. So if I. Why this thing does not disappear automatically? Let me, okay, let me skip. Okay, let's not touch it. I hope it works. So this timeline shows a few of, let's say, milestone discoveries and predictions. And the nice thing about this field is that basically first would come some theoretical prediction or kind of proposal, and then would come experimental confirmation. So in a way, theories would lead the development of the field. So we thought, I mean, it's pretty cool for us also to join the community. So we somehow joined in between and actually found a few new interesting materials that got confirmed experimentally, and this is what my talk is going to be about. Okay, so now Okay, that seems to work. So this is just a brief outline of my talk. I will probably not have time to go through everything, but at least I want to show these wonderful materials that we found. But before, I will start with just a brief introduction to the field. Probably here in this community, I mean, you already know quite a few things, but nevertheless, I will try to keep it short. So basically, the whole field of topological materials is about basically topology as a tool to classify band structures, electronic structures of materials. And let's say the easiest start would be the following. So in condensed matter physics, we basically block functions are the workhorse objects. I mean, these are the core objects. And starting from block functions with this chain of mathematical transformations, we can arrive to quantity that is called Berry curvature. And this is pretty much like Gauss curvature, but in momentum space. Now, in real space, we, for example, have the Gauss-Bonnet theorem that tells us that the genus of a surface is some integer that basically classifies all those surfaces. And if we perform a smooth deformation of the surface, I mean, this number doesn't change unless you make another hole or eliminate a hole. So the same in momentum space. And then the equivalent of the genus in momentum space would be the Chern number. Okay, so now, I mean, with the closed surfaces, it works the following way. So, I mean, this would be, for example, Brillouin zone in 2 dimensions for a 2-dimensional lattice. So because of the periodicity of the reciprocal space, you can close the boundary. So this is equivalent to a torus. You have a closed surface, and then you integrate Berry curvature. So that, I mean, that gives you the Chern number. Now, the Chern number actually describes the first topological phase ever discussed. So the integer quantum Hall effect discovered more than 40 years ago. And integer quantum Hall effect means it's you are dealing with a 2-dimensional system, and you need applied magnetic field to realize it. Okay, so now then probably the next important milestone was the model of Haldane, who said, okay, we can actually realize the same topological phase but on lattices in absence of applied magnetic field. So he proposed this model on the honeycomb lattice. I mean, you still need to break time reversal symmetry to realize this phase. And I mean, for quite some time, the Haldane model remained, let's say, a purely theoretical toy, and I would say that we are still lacking proper experimental, let's say, materials realizations of the Haldane model. Then in 2005 came work of Ken and Millet, who said the following. Okay, they proposed this Hamiltonian. So the first one is just the tight binding model, and the second term would count over second nearest neighbors, and basically, so this is the spin operator, and this object here tells you whether your electron to hope to the second nearest neighbor makes a right turn or a left turn. So there is plus or minus 1, 2 possibilities, and this is basically spin orbit coupling. So spin coupled to the orbital motion. Now, this gives a slightly different topological invariant that is defined modulo 2. So the 2 topological invariant 0 or 1. Okay, now, interestingly, this simple model actually does correspond to spin orbit coupling in graphene. So, which basically means that graphene is in principle expected to realize some kind of a topological phase. So this would be quantum spin Hall insulator phase, which means that you would have some kind of an edge states at the boundary of the system, and there is probably some interest in physics. The problem is that spin orbit coupling is a relativistic effect. So basically, in materials made of light elements, it's extremely weak, and basically, in this case, the band gap due to of this topological phase is supposed to be 25 micro electron volts. So experimentally, this is pretty much useless. Of course, people are trying to enhance it by proximity effects and so on, but it's not going to be a topic of my talk. Okay, and then there was another prediction shortly after saying that the same topological phase you can actually observe in a totally different system now based on heavy elements, so relativistic effects would be much stronger. So Mercury Telluride quantum wells, and very soon it was confirmed experimentally in the group of Lawrence Molenkamp. So basically people saw the quantized conduction at this quantum well. So that was the first experimental confirmation of this kind of intrinsic topological phases. Now, in order to calculate this Z2 invariant, so a topological invariant for insulating systems with time reversal symmetry, you actually don't need to do much. If your system has an inversion symmetries, then all what you need to consider a set of time reversal invariant momentum points. So for example, for two-dimensional systems, there would be 4 of them. For all the occupied states, you need to evaluate the parities, take one product, another product, and then if you end up with -1, it's going to be a topological phase. If you end up with 1, that's a topologically trivial phase. Now, that simple formula actually gives you a very good idea where to look for such systems. So first of all, what you need to do, you need some kind of an exchange of states with opposite parities around some time reversal invariant momentum points. So that basically means that you would look for such systems among materials that have band inversion. And then you need the mechanism to open a band gap in such systems. And then spin orbit interactions would be a natural mechanism. So you need band inversion systems with strong spin orbit interactions. Well, if your system lacks inversion symmetry, then you actually need to do something else to find this topological invariance, but I'm not going to stop here. Let's better speak about materials. Okay, now, so the quantum spin Hall insulator phase is defined in 2 dimensions with this one single binary topological invariant. So in K space, you would expect this kind of band dispersion. In real space, you would expect helical edge states, so counter-propagating states with opposite spins that are still related by time reversal symmetry. Now, another important difference with respect to the integer quantum Hall effect is that quantum spin Hall effect can be extended to 3 dimensions. So you can actually observe in 3-dimensional crystalline lattices. Now things get slightly more complex in the sense that instead of one binary index, you now have 4 of them. So altogether you have 16 topological classes, of which one is basically absolutely trivial, and then you would have this kind of Dirac cone dispersion of surface states. That's what you would expect for those materials, and then this basically helical surface states would rope your crystal in real space. Well, that was somehow interesting because if you have such material, then probably this kind of spin momentum locking would allow you to fight dissipation, so basically suppress backscattering. Also for spintronics applications, that would be interesting because charge current is related to spin polarization and vice versa, and so on and so on. So people thought that probably for electronics, for spintronics, for maybe quantum computing, such materials would be useful. And well, the milestone discovered was that your bismuth chalcogenide. So these were really, let's say, first convenient strong topological insulators, and prototypical materials would be bismuth telluride and bismuth telluride. So these materials are actually very well known because bismuth telluride is widely used as a thermoelectric. It was quite surprising to find some really new physics in a material that is so well known. And what you normally observe in these materials is band gaps of around 0.3 electron volt. So I mean, they're opened by spin orbit interactions. They're never too large gaps. And in order to confirm the topological phase, you would basically do angle resolve photoemission spectroscopy to probe the surface states, and that's how you observe dispersion of those topological surface states. So that's basically the proof of the presence of topological phase in the bulk. Now, of course, it's not only about bismuth telluride and bismuth telluride. A few other bismuth-containing ternary materials were discovered later, but they're actually all very similar. So they all have some kind of layered crystal structure, and the dispersion of the surface states would also be very similar. So it's always graphene-like single Dirac point at the gamma point of the surface Brillouin zone. So quite a few materials already known. Now, speaking about spin orbit interactions, so so as I already mentioned, spin orbit interactions are a relativistic effect, and normally you would, let's say, from the textbook exercise, you would expect the strength of spin orbit interactions to grow as z to the 4th, but this is actually formulated for the hydrogen-like atom with only 1 electron. For real atoms, this is more like z square if you go along the vertical direction of the periodic table. And I asked my postdoc actually back in a while to calculate spin orbit splittings in the valence shell of a number of atoms, I mean, basically of the entire periodic table. So the different colors correspond to different shells as you fill. So every time you fill new shell, you sort of reset the trend, but you can see how the strength of the spin orbit splitting grows, and bismuth is here, right? So this is number 80. I forgot what's the number, but the next one is polonium, right? So bismuth is basically the last element in the periodic table that still that is made of stable isotopes. With polonium, of course, you're not going to deal anyhow experimentally. So bismuth here is for a good reason in these materials, because this is really, like, let's say, practically the strongest spin orbit interactions you can get. And also it realizes a diversity of crystal structure, so that's a nice material. And basically, also all these topological phases you can easily reproduce computationally. So for example, these are the calculations of band structure of bismuth night without spin orbit interaction and with spin orbit interaction. So it happens that when you basically switch on spin orbit interactions and calculations, we can easily switch off and switch on relativity. So it's a kind of Gedanken experiment, but nevertheless nice to play with. So in absence of spin orbit interactions, your material is actually just normal semiconductor with a small gap. But once you introduce spin orbit coupling, it actually exchanges the bismuth containing conduction band and selenium containing valence band that are made of pi-z orbitals of those atoms, and it closes the gap, so it goes into a band inversion regime in a small region around the gamma point. Okay, so, and actually the band gap even in this case corresponds well to the experiments, which is unusual for DFT. Why? Because the band gap is due to spin orbit interactions, and spin orbit interactions in our calculations are actually relatively well reproduced. Okay, so coming back to this slide, we joined somewhere here, and what we started doing. Okay, we were not the only people to do this, but nevertheless it brought us some interesting fruits. So we decided to go and do high throughput computation. So basically, for, let's say, all known crystalline structures. So if you think about this, it's actually not such a huge amount. So for example, you go to ICSD, International Crystal Structure Database, to COD, which is crystallography open database. You basically extract all the data, you clean it a little bit to remove duplicates or whatever crystal structures with fractional populations, because we cannot calculate them. You end up with just over 100,000 unique crystal structures. If you tell this to an organic chemist, people will laugh. I mean, it's not even big data by any standard, right? You can just take and do DFT calculations of a big portion of this materials without any problem. So this is what we started doing. You basically calculate band structures, you calculate topological invariants, you get a database, and basically, if you find something interesting, then you can come to your experimental colleagues and ask them to do something. So actually, all our data is publicly available for already many years, and this is, as I already mentioned, not the only database that exists, but nevertheless, people are still finding something useful. So you can easily access it on Materials Cloud portal. I mean, there is a search form. You can put stoichiometry or space group or any other kind of field, and then you go. I mean, there is band structure information about topology. Let's say a reference to the original ACSD data entry or to the paper. I mean, it's kind of organized. Okay, so the first actually material that we found early, something like in 2013, was this bismuth iodide. Okay, so this is quite a bit different from bismuth night and bismuth telluride that were known back then. So what you have here, you have those graphene-like stripes, one-dimensional, that are made of bismuth atoms, so blue atoms, and those are iodine atoms. And this is packed in three-dimensional crystal. So it's a kind of a quasi-one-dimensional structure. And why it attracted our attention? Well, I mean, because DFT calculations would predict it's a weak topological insulator. So this is the band structure. I mean, a small band gap of 0.14 electron volt doesn't matter. And then the topological phases, because of the band inversion at two inequivalent time reversal invariant momentum points. Now, when people see this band structure, they always say, no, there must be something wrong with your calculations, because your bands don't cross anywhere. I mean, that looks totally like chaotic spaghetti. Probably USCF did not converge. Well, I have to say that it's all good with this band structure. So what happens here is that when you have spin-orbit interactions naturally lift band degeneracies. When you have spin-orbit interaction that are as strong as your Hopin parameter, I mean, as large as the bandwidth, it's all messed up. It looks very chaotic. So it's all fine. I mean, it's very typical for all these bismuth compounds. And now, what would mean weak topological insulator? So you can think of this as a stack of two-dimensional quantum spin Hall insulator phases along the third dimension. And that basically means that you would have a surface that states that that originate from the edge states on the side surfaces, and top and bottom surface would be gapped, right? So on the side surfaces, you would expect this band dispersion instead of the cone. So one direction is linear, another direction is like weak dispersion. And then basically DFT calculations would tell you something like that. So there would be these gapped surfaces, 0, 0, 1, and then there would be the other ones would have dispersion that we decided to call Dirac groove in this work. Okay, so far so good. So now this was our prediction. We came to our experimental colleagues, and of course the first thing you need to do is to do material synthesis. And fortunately enough, I had a colleague who actually knew exactly how to synthesize this bismuth halides, Anna Yazyev. So back then she was in Dresden, now she's in Amsterdam leading her own group. And then basically, well, I can make it for you. And then she sends me ampoule with the crystals. You know, I'm a theorist. I mean, I receive a sample. I get so much excited. So these crystals are actually very tiny. They're like maximum 3 millimeters long and very fragile. So very, very tricky to handle. And then, of course, I started annoying all my experimental colleagues coming with the sample and basically poking in them and look, I mean, let's do something with this. I got a sample. So we did some kind of basic characterization. So TM would show, okay, I mean, it's actually a very nice crystal, very little disorder. I mean, they're small, but very pure. You can also do transport measurements. It does show that it's a semiconductor with narrow gap. So you can basically go to the intrinsic regime, measure some activation energy. What happens around 100 Kelvin, we still don't understand, but at least it will show insulating dependence of conductivity on temperature. And then, of course, now if you want to show it's a topological material, you need to do ARPES. I mean, for bulk materials, I mean, this is the way it works. And of course, many people would simply decline working on such sample. You know, I mean, you really need to find someone motivated. Unfortunately enough, I had a colleague who was motivated enough, Luca Marischini, so one of our former PhD students at EPFL, who at that time was working at LS in Berkeley, and he basically measured, and then he wrote me an email. You know, but I think I see something. I'm not sure this is what you're looking for, but I mean, here's the picture, and he sent me this. And well, I mean, that looks like very cool, right? I mean, it's a very nice crossing with the crossing point very close to the Fermi level, very well done. I mean, and then you can even dope some potassium on the surface. You can expose this crossing a little bit more. So this is a real crossing, not just the top of the band. Well, I mean, we thought, well, fantastic. I mean, here it is. And then when looking closely at the data, we realized this is actually inconsistent with our theoretical predictions. Why? Because the crossing that we are observing is actually observed for the surface that is supposed to be gapped. Okay. And then it's not, strictly speaking, this Dirac groove dispersion. It's more like a very much stretched Dirac cone that we saw. Well, how to solve this problem? Whom to blame? Well, you would blame DFT calculations in this case. So what's the problem with DFT? Well, DFT is a kind of a very convenient scheme, but it's formulated for the ground state properties. Ground state properties means like cohesive, vibrational, magnetic. It doesn't work so well for the excited state properties, and which means not just optical, let's say, spectra, but also photoemission properties, which basically means what you're measuring in ARPES, the quasi-particle properties. Well, you need to do something better than DFT. So in DFT, the whole complexity of electron-electron interactions you would sweep under the carpet, put in this term that depends only on the density, so the exchange correlation potential. If you want to do better, you need to replace it with something more meaningful. So let's say one step towards something better is to replace it with energy-dependent self-energies, and the practical scheme for doing such calculations is called GW. Okay, so these are calculations we could still do for such system, and typically DFT would severely underestimate band gaps of insulating materials. And I mean, this underestimation is very much unpredictable. So for example, in DFT, germanium is a metal, right? And some other ones, probably the band gap is smaller, but kind of still reasonable. So you never know. So GW at least helps recovering this deficiency and provides band gaps, I mean, even the simplest schemes in reasonable agreement with experiments. So this is what we did. Now we have to realize that we are dealing with band inversion materials. So if you are thinking about band inversion, that basically means that DFT would overestimate the region in momentum space where band inversion happens. So what GW does, GW is supposed to pull conduction band of the valence band, and that reduces this volume and momentum space when band inversion happens. So what happens in this particular case, we start with our DFT prediction, so weak topological insulator, and the band inversion is due to, the topological phase is due to the band inversion at 2 time reversal invariant momentum points. Now you reduce this volume, and what happens is that with GW calculations, you actually eliminate inversions at one of these time reversal invariant momentum points. So instead of having open volume and momentum space where this happens, you close this this volume, and that's basically some kind of a discontinuous topological phase transition. So what you get now is a different topological phase with different Z2 numbers. So now it's a strong topological insulator with those indices. We still have some very small band gap, and if you now recalculate our surface states for this surface that was gapped before, 001 surface, we're now getting those pictures, and basically we expect anisotropic Dirac fermions as topological surface states. Okay, so now with this, we can play a little bit further with this idea. Of course, if you continue pulling the conduction band, you would eliminate band inversion altogether. So this becomes a trivial insulator. So essentially, I mean, this would be a topological phase diagram. So from this phase, we are going to that one, and basically this is where our DFT calculations would be. So this is band gap versus this kind of a quasi-particle shift, and GW puts us somewhere here. Okay, so now new predictions for the surface state dispersion against experiment. Now the agreement is actually very good, so we were very happy. And one of the referees was not very happy, and the reason is that, okay, now actually the band gap is very small in those materials, right? And what I'm showing here is the energy range of almost 1.5 electron volts. So actually those are bulk-like states, and the crossing the surface states, they live somehow in this small region. I mean, so this was done at the synchrotron at ALS. I mean, and the referee is not him. No, you need to really to show the surface states. So the only thing we could do as a step better is to do the laser-based TARPS with a tabletop system that provides much better resolution and momentum, and we still see nice crossing without any gaps. So we concluded that these are the edge states, and the referee was finally made happy. So altogether, we have put this in one single publication, and I mean, I was basically very happy. So this is me as the last author. My postdoc who did all the calculations, I mean, he's the first author, and in between all the experimentalists. So we finally made it to lead some kind of a big series experimental effort that brought some fruit. So I have to say that it was actually very exhausting to compile all this stuff in the publication and fight with people who is going to be the first author. So I had to defend my postdoc quite a bit in this position. Anyway, I mean, that of course advanced a little bit, even though these materials, I mean, did not become something that would find practical applications. Nevertheless, I mean, it's an interesting family of topological insulators that is different from the let's say from the existing ones. I mean, first of all, I mean, the surface states would be anisotropic. There are some other topological phases, and I mean, materials-wise, it's a family of materials. So there is bismuth iodide, there is also bismuth bromide. So I mean, the building blocks are the same, but they packed in crystals in different ways. So these crystals have different symmetries, and respectively, then they realize different topological phases for more like symmetry reasons. And then there are also mixed iodine bromine halides. I mean, that extend these families further. So there are quite a few materials that are actually very interesting to study, including higher order topological materials, quantum spin hole insulators when you strip this down to thin layers, and so on and so on. Some other people are doing this. We are mostly done. Okay, so the other example I wanted to show are the two Weyl semimetals that we found. So what are Weyl semimetals? These are topological phases that don't have any gap. So instead they have degeneracies between their conduction and valence band that are point-like. And these points, they have distinct chirality. So if you would probably basically enclose your degeneracy by a sphere, let's say depart slightly from the energy of the degeneracy and calculate Chern number on the sphere, it would be a non-zero Chern number. Okay, so they always come in pairs of opposite chirality, and well, I mean, they are supposed to have some kind of distinct manifestations of topology like fermionic surface state, so people would expect anomalous magnetotransport like current anomaly. And basically those also come into flavors, type 1, which is, let's say, think of graphene dispersion, but in 3 dimensions, and type 2, which basically occurs when you start tilting the Dirac cone. And then at some point, the constant energy surface open up, so from something that is like close to you go to something that looks like a hyperbolic. And this is what Alexei Sudanov unfortunately passed away, let's say, proposed to call them type 2 Weyl semimetals. Okay, so basically the initial proposal was tungsten ditelluride and molybdenum ditelluride. Tungsten ditelluride is, let's say, still somewhat under question mark, and we just wanted to find some other materials. And the materials that we found were diphosphides of molybdenum and tungsten. And those materials actually have nothing to do with layered crystal structure. So it's actually a quite complex 3-dimensional crystal structure with some non-symmetric symmetries, quite a mess. So basically, it was known how to synthesize them. I mean, that's why they appear in the databases. And then the calculations would tell you if you just plot the band structure along some high symmetry paths. I mean, okay, so this would be your electron pockets, those would be your hole pockets, quite large pockets, so it's a semi-metal. Now, if you look into, let's say, into the entire Brillouin zone, you find that this valence and conduction band pockets, they are connected by 4 pairs of Weyl nodes in KZ equals 0 plane, not too far from the Fermi level, and the distinct point of those materials, why they would be different from other known to Weyl semimetals, like for example tantalum arsenide or the same tungsten ditelluride, molybdenum ditelluride, is that the distance in momentum space between the Weyl nodes of the opposite chirality would be unusually large. So we know why is that. I mean, there is a physical mechanism for this, but the consequence is that then you would expect many of the, let's say, responses that result from this topological phase to be much stronger, to be sort of exaggerated. So we decided to call them robust Weyl semimetals. Okay, and then of course comes prediction. For example, in this case, you don't know how these materials cleave. They're not layered. You can suggest different surface terminations, calculate the Fermi arcs, so you'd find the Fermi arcs. But of course, let's say the dispersion of these Fermi arcs would depend a lot on how exactly you are going to terminate. So that's actually somewhat a problem. Now, we of course wanted to have these materials also synthesized. So we contacted 3 different groups, and no one actually succeeded to reproduce what was published in this paper, in these old papers. So we gave up. We published a paper that had only theoretical results, and somehow soon after it was published, a few other experimental groups actually managed to make those materials, notably the group, the Institute of Claudia Felser in Dresden. So they did, and what they found was actually very interesting. I mean, this slide somehow summarizes these first results, mostly from the first paper of Claudia Felser. So, so tungsten diphosphide actually happen to have unusually high low temperature conductivity. So then basically at room temperature, of course, the conductivity much smaller. And then for experimentalists, the measure, let's say, of ratio of 1 with respect to 2, so 0 temperature limit with respect to the, let's say, ambient temperature would be residual resistivity ratio. And these materials would show unusually high residual resistivity ratio. So they were claiming, I mean, it's absolute record for binary compounds, so for anything that is not elementary. So experimentalists typically take it as a measure of purity of materials. At the same time, these materials would show very extremely high non-saturating magnetoresistance, so up to, let's say, gigantic magnetic fields of 63 Tesla, they would measure 200 million %. And it's interesting on its own, but it's also very unusual to see this together with high low temperature conductivity, because normally these two properties are mutually excluding. They also claimed for a mean free pass of 0.5 millimeter. Well, probably that was a little bit of an overestimation, but it's kind of interesting to see in material that you don't really spend much effort on making it very pure. Actually, these materials are not even exactly stoichiometric. Nevertheless, you immediately have something like this. They would also show hydrodynamic electron fluid transport regime at low temperatures. There is even a preprint that is basically claiming negative resistivity. Well, with magnetic field applied along the current direction, but nevertheless, it's kind of a very weird plot. So that probably also results maybe from the hydrodynamic transport, because when your charge carriers move in hydrodynamic regime, I mean, there might be some kind of vortices and, I mean, backflow of the charge carriers. So there are alternative explanations for this. And when you look at all these properties, it's actually absolutely not clear how they would result from a topological phase. There's absolutely no direct connection. That said, of course, once the samples were available, we together, well, our colleagues at Polytechnique Institute, I mean, they of course did ARPES, and they would basically find all these Weyl nodes, I mean, in the ARPES measurements. Okay, I mean, these plots I hate. I mean, to me, I mean, it looks very bad, but for the experimentalists, no, this is absolutely fine as a data. And in this case, DFT calculations actually seem to work very well. So when you're dealing with metals, with semimetals, typically DFT seems to be a lot more reliable tool than for insulators. Except for some delicate cases, like, for example, tungsten telluride, I consider a delicate case. So now the only property, the property that we actually managed to sort out was in all this, let's say, list of unusual things, was the non-saturating magnetoresistance. Okay, so basically, so this is a plot of the non-saturating magnetoresistance for the along certain, let's say, field direction, and it's almost parabolic, no quantum oscillations until 63 Tesla. And the reason that, okay, I mean, the Fermi surface pockets are actually very large, so you would need probably higher fields to reach the quantum limit. Another interesting thing is that so it doesn't saturate anyhow at up to 63 Tesla. And another interesting property is that when you start changing the direction of your magnetic field, you would suddenly kill this effect. So this is what people call anisotropic or angular magnetoresistance. It would show this kind of a diagram with very strong magnetic resistance and virtually no magnetic resistance for an orthogonal field direction. Okay, so we wanted to understand what is going on, and actually, if you think of magnetic resistance, so the first picture, I mean, this is taken, I think, from Ashcroft-Mermin, just tells you about, let's say, orbits in real and momentum space, when you basically have semi-classical approximation, your charge carriers in magnetic field. So let's say the mechanisms that can underline non-saturating magnetic resistance, first of all, this is charge carrier compensation. So if you take just normal, let's say, free electron gas, or the magnetic resistance would be zero. Why? Because Hall voltage compensates basically the Lorentz force, so the magnetic resistance would be zero. Now, if you have two equal pockets for electrons and for holes, basically this compensation is broken down, and now you're going to have non-saturating magnetic resistance that is strictly quadratic. But I mean, for this very much model situation. Now, if you basically for example, introduce such changes to the band structure that makes your electron and hole pockets unequal, then okay, this magnetic resistance is no longer quadratic. It's probably somehow less than quadratic, and at some point it would saturate. Now, another mechanism apart from this charge carrier compensation would be open orbits. If you have open sheets of Fermi surface, then for some magnetic field directions, you can also expect non-saturating magnetic resistance. So, I mean, these are very much textbook examples. And in my group back then, I had this couple. So Shang Wu, who initiated this very popular software package Vanyatool. Now he's back to Beijing, and his wife Nanzan. They actually implemented in this in their package Boltzmann transport approach for magnet resistances and the relaxation time approximation. And what you're basically doing, you're doing DFT calculations. You start with basically realistic Fermi surfaces and all the Fermi velocities on those Fermi surfaces. You do explicit numerical calculations for all these transport properties in applied magnetic field. And we actually had lots of fun just going back to textbook examples and trying to see what it gives. For example, this is well-known Fermi surface of copper. This is how angular magnetic resistance would look like. So you have magnetic field and current, you rotate your magnetic field, and basically the conductivity changes. It has this kind of a very funny shape. And back in the days, let's say 60 years ago, people would have lots of fun explaining this, modeling Fermi surface sphere plus some cylinders and doing all sorts of analytics. And now with explicit calculations, we can actually reproduce this exactly. We can go to any point and tell why, I mean, it goes up here, goes down there. What is the contribution of these different mechanisms, charge carrier compensation versus open orbits, and so on and so on. And I mean, now it was actually very interesting to have a new look on the textbook examples. Yes. What do you mean anomalous velocity?
The vector product between Berry curvature.
So I have to say that in these calculations there was no Berry curvature. And even in the calculation, so I mean, at that time it was simply not implemented in the in the package. So for copper, I mean, this would not play any role. For our material, that there is one caveat, but I will come back to this. But it's actually a very good question. So, and yes, okay. So, and then of course we go back to our material, and this is actually how experiments look like for the anisotropic magnet resistance. We also reproduce this nearly quadratic, I mean, a slightly different exponent, but the difference is very minor. And this is what theory predicts us. Okay, so I open my microphone. So once again, so the theory is totally consistent with experiments, and we can explain. In these calculations, we didn't have any Berry curvature. And in principle, I believe we could neglect this simply because if you look at the Fermi level, it actually happens that these Fermi surface sheets, even though the Weyl nodes are not far away from the Fermi level, I mean, they actually carry zero Chern numbers. So at the Fermi level, undoped material is actually not so much topological at the Fermi level. Nevertheless, it does show those things. And the interesting mechanism for this for this extreme angular magnet resistance behavior is the following. So if you have concave segments of the Fermi surfaces, actually, because of the way the Lorentz force works, I mean, your charge carriers follow the opposite sense of, let's say, of revolution, of rotation. So essentially, for let's say for the magnetic field direction where we observe strong magnet resistance, electrons, and holes are holes. Now, if we switch our magnetic field direction to along the C-crystal graphic orientation, hole carriers start following electron orbits, simply because, I mean, let's say there is more abundance of those concave segments. And it's a kind of, and then of course you break down the compensation because you have electrons plus electrons, so it becomes a normal metal, I mean, which was a fine mechanism, but I mean, it simply means that all what we are discussing simply follows from the let's say, from the shape of the Fermi surface. This is just a phenomenology, absolutely nothing to do with the topological phase, except for one thing. So we are doing relaxation time approximation, which basically means that we just assume constant relaxation time, and all the results of the magnetic resistances we plot as a function of b times tau, the relaxation time. Now, if you want to gauge, for example, this 200 million% observed experimentally to the theory, I mean, it brings you to the number of relaxation time of 10 to minus 9 seconds, which is, let's say, not extraordinarily long, but quite long. then you would ask yourself, okay, maybe this is because, I mean, there is some kind of a topological protection of my electronic transport, which basically suppresses the scattering of just normal bulk charge carriers. Maybe, but there is absolutely no proof for that. Okay, so do I still have maybe 5 minutes to conclude this story? Okay, very good. So I wanted to conclude with the following. If you look in our database or in any other database on topological materials, what people are saying is that, okay, about 1/4 or 25% of materials are somehow topological. There is something topological going on in them. Even though from the experimental point of view, probably very few of them would be interesting. So, I mean, that's an interesting statement. And I mean, I just want to give you a demonstration of you can find something topological even in very ordinary materials like BCC iron. So, I mean, topological band degeneracies like Weyl nodes, you need, I mean, originate in band structures for two reasons. Either you break inversion symmetry or you break time reversal symmetry. Well, time reversal symmetry, which means any magnetically ordered material. And if I take, for example, BCC iron as an example, well, I mean, so this was not done by me, but by my postdoc during his previous appointment, Daniel Gazalbes Martinez. So when he was with Ivo Souza and David Vanderbilt, they published this paper. Okay, so this is the band structure of ferromagnetic iron. You have magnetization along a given direction, and then actually there are plenty of Weyl nodes, I mean, at the band crossings in this band structure. You see, there are sometimes the crossings are lifted. There, I mean, lifted degeneracy because of spin orbit. In iron, it's not as strong like in bismuth, so you do have some kind of avoided crossings, but the gaps are not small. But sometimes they do cross, and these are true Weyl nodes. So this is just a table, let's say, between the bands 6, 7, 9, 10. I mean, not far from the Fermi level. I mean, you can categorize, find locations of all those Weyl nodes, the energies, and yes. Yes, yeah, that's the Fermi level. So, okay, now we decided to see, would there be any kind of experimental signatures of those topological band degeneracies in iron? So that was our question, and when Daniel moved to my group, this is what we started doing. So this is how Fermi surface of iron look like if you break down into individual sheets. And it happens among all these sheets. I mean, there are some larger ones. There are a few of them tiny ones, and two of them for this magnetic field direction, I mean, magnetization direction. They have they enclose Weyl nodes, so that would give them Chern numbers of +1 and -1. Okay, so there must be some kind of Fermi surface arcs that you could probably observe in RPS measurements, even though doing RPS measurements on magnetic materials is, of course, very difficult. Okay, now you can categorize, you can find those Weyl nodes. I mean, so they're actually very close to the Fermi level. So there is one single, one double Weyl node. You can actually even find nodal line. I mean, it's actually from the topological point of view from the point of view of topological band degeneracy, it's actually a very complex material, just BCCRN. And then, of course, if you want to find those Fermi arcs, you would, I mean, so this would be, let's say, the band structure, the spectral weight projected on the Brillouin zone for 110 surface, I mean, which is totally fine for iron. And you would need to look into this small red square, and in this small red square, you'll find this. Okay. So, and this would be this Fermi surface pocket that encloses the Weyl node. So it actually works in a very complex way, because this this chiral pocket as such, I mean, is overshadowed by a very large pocket. So this, if you call this a Fermi arc, I mean, it's a more like a Fermi arc resonance. So it's not really a state. But then it goes into this large topologically trivial pocket, and then, I mean, via another pocket it connects. So this would be, let's say, a true Fermi arc, but it works in an indirect way. And then, of course, since we can easily rotate magnetization in our iron, we can actually use this as a degree of freedom to trigger the topological phase transition. So basically, we start with two Weyl nodes of double chirality of -1. Then we start tilting magnetic fields. So this one actually dissociates in two. Then one of the counterparts migrates and annihilates with this other Weyl point with the opposite chirality, which is pretty cool. And then in the band structure, you can, of course, see all these changes. And I mean, this is what in principle should be observable in iron. I have to say that looking in such a small region in momentum space with RPS measurements done on magnetic material is experimentally challenging. So for now, no one still confirmed these predictions, but it would be fun to see this. To see this. As far as I know, actually, people do confirm the presence of this small Fermi surface pocket, that it does exist in iron, but now the question is observing this Fermi arc. Okay, so I mean that was just, let's say, a small conclusion saying that topological degeneracies or topological phases are actually quite abundant in materials. Doesn't mean that these materials would be very beautiful or very useful. So it's more like a question of finding material that would have very, let's say, favorable experiment from the experimental point of view of properties, and where this topological features would not be overshadowed by, let's say, bulk charge carriers. The problem with bismuth selenide is that even though there are surface states, there are so many bulk charge carriers that, I mean, it's hard to measure anything separately on surface states. And the same for iron. I mean, you have this tiny topological Fermi surface pockets, but then you have huge trivial topological Fermi surface pockets. So observing something, let's say, separately from trivial would be very difficult. Okay, with this I would like to thank a number of people, my group members first of all, and all the colleagues who helped us, and of course a few funding sources, and you for your attention.
Anyone's got questions? Far away. There's nothing on the chat.
For this metallic material, am I right that it is metallic magnetism? So you have spontaneous spin polarization.
So iron, yes, of course. So when okay, so you can see this in the band structure, because basically the spin quantum number is color coded, right? So you red, let's say, spin down, blue spin up, but then of course because of spin orbit, Z is not a good quantum number. So whenever you have, let's say, this crossings, so avoided crossings, so when bands are close to each other, you have, let's say, a spin quantum number that is somehow intermediate. So I mean, that's why they start mixing. But most of the time, yes. Yeah, no, exactly. Because in iron you can, of course, I mean, simply use the Stoner criterion to explain the magnetic order. Yes.
Have you also found out, just like in boron bismuth iodide, that the effect of GW was very important? Are there also other materials where the effect of GW?
So I can tell you, for example, about bismuth selenide and bismuth selenide. For example, for bismuth selenide, when you do GW calculations, it doesn't change the topological phase. So because bismuth selenide is so much deep in the band inversion, and then if you actually do GW calculations, you do reduce this the volume in momentum space where band inversion happens. Yet this doesn't change the band gap. Okay, simply because, I mean, it's mostly spin orbit. On the other hand, for bismuth telluride, which has somewhat different band dispersion, GW calculations do change the band gap. I mean, it's a kind of a delicate interplay between spin orbit gap and whatever, let's say, the band dispersion. And for molybdenum diphosphide, tungsten diphosphide, we simply did not do any GW calculations. I mean, once basically experiments showed us that the Weyl points are pretty much at the energies we would expect them.
So that will be seen in hybrid calculations.
Yeah, okay. So we did GW calculations on bismuth chalcogenides. Other people, I mean, there is a Chinese group that was also active in this about the same time. They actually did hybrid functional calculations, and I mean the effect is pretty much the same. So there are some differences with respect to GW calculations in terms of band dispersion, but it also brings. I also have to say that there are even people claiming that bismuth iodide is still supposed to be actually weak topological insulator, but it might be sample dependent, you know. Some.
One question, so related to GW, right? My understanding was that, okay, you have this prediction on the ground state of the system, right? That you can say that with DFT calculations. But then when you do RPS, you perturb it, right? Because you're doing
some measurement,
right? You're shining light. would that apply also, for example, when I want to use that material in an electronic device, or I do a transport mechanism, where I perturb it with an electric field? Would that have would that mean that maybe biomaterial where DFT predicts that it's topological, but then I use it in a device for an application?
Oh, I mean, let's say whatever happens in electronic transport, I mean, it's the same story as, for example, for emission intensity. So one have to use DFT very carefully. You see, I mean, because in DFT, when we are plotting the band structure, I mean, this is not true quasi-particle band structure. These are Kohn-Sham energies, and Kohn-Sham energies, let's say, there is a missing link. Right, because I mean, quasi-particle energies, they know some kind of excitations, and Kohn-Sham energies are sort of just Lagrange multipliers. Nevertheless, I mean, very often let's say, very often, even if the band gap is slightly off, we do know that DFT, let's say, reproduces well band dispersions in most cases. So, it becomes a little bit let's say, not very rigorous science, but it's a very useful tool. Yeah, we have to be careful with this. Of course, if you're able to do GW calculations, then you should do them. I mean, the problem is that, I mean, these calculations are typically much more expensive and not even possible, I mean, for relatively large models.
It's very nice talk. I have a very naive question. In the constant diphospphide material inside the MR is only related to the shape of the firm surface, not the topology, because the topological band is very far away from. Well,
it's not very far, but it happens that probably doesn't play any role anymore.
Yeah, my question is, how far is far enough to decide these bands that's not related to the.
This has to be assessed individually in every case. So basically, what for example we do for this material. Okay, so let me come back. I give you exact numbers. How far is far? How far is far? It says. Yeah, so this is something like 0.3 to 0.4 electron volt, right? So W1 at 0.3 and W2 at closer to 2.4. I mean, I probably had these numbers somewhere. Yeah, right. You can see them. You can see them here, right? I mean, so this is the energy scale. Now, I mean, of course, I mean, you might say, I mean, this is not too far. I mean, all the time I see papers where people discuss some topological degeneracy at -1, -2 electron volt and so on, some deeper. And of course, I mean, if you do ARPES, I mean, it's easy for you to do, but in the transport measurements, I mean, there is no way this can manifest. What you have to do in this case, you shouldn't really ask yourself how far in energy is this is this topological degeneracy. The question is, let's say, what's the Chern number of this Fermi surface pocket that is at the Fermi level? So in this case, this is actually, I mean, the Fermi surface pockets happen to be topologically trivial. That said, of course, when we do calculations, I mean, this is a material without any intrinsic doping. Experimentally, they are very often off stoichiometric, so there are some kind of Fermi surface variations, and I can easily imagine that it finally pushes you at some point to the regime where you start having non-zero Chern numbers for the Fermi surface pockets. Yes.
Thank you very much. Do you have any predictions for getting these type 2 files down so they have
we don't have any predictions. I've never seen this done experimentally, and I guess this would be somewhat tricky because these are not really layered materials. And I don't know if it's possible to grow them somehow with MB in a kind of controlled way. No clue. So normally, I mean, this is a kind of I don't know, synthesis that gives you crystals, I mean, but not in film deposition or anything. And I also have to say that even despite the fact that the Weyl nodes were observed in ARPES, I mean, there is no observation for the Fermi arcs for the same reason. I mean, because there is no way you can prepare a nice, well-defined, clean surface of this. I mean, they simply don't cleave nicely. And if you have disorder on the surface, I mean, the whole thing of the Fermi arc, I mean, the dispersion of the Fermi arcs becomes ill-defined. because the dispersion of the Fermi arc is not given by the bulk topology. It's given by the local surface. What is given by the bulk topology is the endpoint and the start point of the Fermi arc. So basically, but if you have, let's say, this is your in and out, right, and you have any kind of dispersion in between, then I mean, basically, you don't observe what is in between. It's totally washed out in the spectral weight.
All this topological classification, right? It relies on single electron block functions.
Yes.
But now your timeline had some instances of correlated.
Yeah. Well, I mean, there is one very much disputed case. I stopped following this, but I mean, there is this topological condo insulator thing, which is samarium hexabride. I don't know. There were many disputes, many papers. Sorry, I stopped following this already quite a few years. So I don't think it was ever finished. And of course, on this timeline, it's not complete. You know, it's just one PowerPoint slide. I cannot pack as much as one. But of course, I mean, there are also quantum anomalous Weyl insulators. I mean, there are also, I mean, now with all this more superlattices, I mean, there are people discuss also fractional topological phases, and this seems to be reality. But
so without talking even on SMB6, can you generalize some kind of topological classification based on many-body wave functions that would still apply for systems where you have high, large U's? And I mean, there are a lot of materials where the single electron wave function picture will break down.
Well, I mean, many people would like to have this. I mean, there are several proposals how to define topological invariants. I mean, starting not from single electron for block functions, but I mean, maybe from Green's functions or some kind of alternative approaches. I cannot tell you which of these approaches is good or which is bad, and I mean, I also cannot tell, I mean, which of these approaches would be practical, let's say, because I mean, let's say as theoretical concepts, I mean, many of them are actually very good. I mean, if this is something that you can do in a high throughput way, calculate plenty of materials and classify them, probably we are not there yet. Well, that said, if you are speaking just about you should remember there's also DFT plus U. I mean, that somehow allows to deal with correlations in Pullman's way, and I mean, and there you can apply the same machinery for the classification starting from single particle wave functions. Any questions on Zoom? Or no? Okay.
The UNSW guys are saying, "I'll see you in UNSW." So I think
Okay.
when you get back up there. But I'll just hang on. Let's stop record.